And start. So, hello everybody, and welcome to the contributed talk session of this week. And it's my pleasure to introduce Pierre-Olivier Parisé from the University of Hawaii. And so, please, Pierre-Olivier.
Thank you, Antone, maybe. So aloha from Hawaii. So I've been recently a temporary assistant professor here in Hawaii. So first I want to thank all the organizers that first invited me to give a contributed talk in the week on the Branges-Rovnyak spaces. And also overall, I want to thank Javad and Iliad for organizing this big focus program. So thank you for all the organizers. I know that there's a lot of energy in this and preparing this type of event. So thank you very much. And I'm learning quite a lot from these little talks. So this has been said, today I'm going to talk about summability in the Branges-Rovnyak spaces. So this is a joint work that I did with Javad Mashregi and Thomas Ransford while during my PhD thesis. So I'm gonna talk of the summability of the Taylor series, in fact. So we're gonna see in the Branges-Rovnyak spaces that there's some like surprising fact related to this. So what we're gonna deal today with is the space of holomorphic function. This is the main topic of this program. So the space of holomorphic function would be the function which you can expand it as this Taylor series, and we will equip it with the uniform convergence, the topology of uniform convergence and compact subset of the unit disk. And for a function, we will define its Taylor polynomials by this expression here. So we just truncate the Taylor series of the function and we get Sn of f. And so, sorry, it's my phone. That just rang. So the SNF would be the Taylor polynomials. And so a question I want to study today is, does the sequence of Taylor polynomials converge to f in a certain sense? So there's three directions we can take. We can look at the pointwise convergence on the unit disk, but this it's quite easy because from standard complex analysis results, we know that the Taylor polynomials will converge to the function. So there's at least nothing to do here. And we can look at the pointwise convergence when we push to the boundary of the unit disk, and the Taylor polynomials behave quite widely if you put f in different spaces. Like if you take the disk algebra, we know from a Dubois-Reymond construction that if you take the at some point the Taylor polynomial will diverge to infinity. So the Taylor polynomials behave quite like widely when you approach a boundary. So I don't want to go in this direction today. I want to go into norm convergence. So we're going to be given a space of holomorphic functions, in fact, a Banach space. So we're going to have a norm on the space of functions, and we're going to look at the convergence. And today I want to really to concentrate on one specific space, is the Branges-Rovnyak space. So what is the Branges-Rovnyak space? So we're going to denote B sub H infinity, the closed unit ball of H infinity. So H infinity is the bounded functions on the unit disk, holomorphic functions. So if we have a B which is in the closed unit ball of H infinity, the Branges-Rovnyak space HB is the subspace defined by this condition. So it's the space of holomorphic functions on the unit disk such that this quantity is finite. So there's like multiple ways of defining the Branges-Rovnyak spaces. I chose this one because I can put it on one line. The other definitions, you need some several like Toeplitz operators, or you need to know some stuff on reproducing kernel Hilbert spaces, which is by the fact the course of Javad Mashregi, who is given right now. So if you want to know more about reproducing kernel Hilbert spaces, you can attend Javad course. So I chose this definition. So if you equip with the following norm, the space HB here, you get a Hilbert space. If the norm of B is less than 1, the h infinity norm of B is strictly less than 1, then HB is just a renormalization of H2. And when B is inner function, then HB is the model space. So there was a weak on the model space. So yeah, so if you put like B is inner, you can do here the calculations, you will get the norm of F exactly. And so so here we're gonna, in fact, if you do the calculation, you're gonna see that F must be perpendicular to every G in H2. And so you got the model space, the definition of the model space. BH2, in fact. So in general, we always have that HB is a subset of H2, but HB is not necessarily closed in H2. So HB inherits its own norm to become a Hilbert space. So there is like two subclasses which are important for the theory of the Branges-Rovnyak spaces. So when B is the closed unit ball of H infinity, the following assertions are equivalent. So B is a non-extreme point of B in H infinity. Equivalently, there's an equivalent thing for non-extreme point of B infinity. A characterization of these points is when the function log 1 minus mod B squared is integrable on the unit circle. The set of polynomials is contained in HB, and the set of holomorphic functions, which are holomorphic up to a neighborhood of the unit disk, is contained in HB, and the set of polynomials is dense in HB. So all these assertions are equivalent. So our question then makes sense. So when B is non-extreme. So I suggest that for the extreme case, I recommend you that you attend Bartosz Malman talk. He will speak a little bit about this. So now the question that the specific question I want to ask is, do the Taylor polynomials of the function f in HB, when B is non-extreme, converge the function f in the norm of HB? So this is the question I want to ask today. So since the polynomials are contained in HB, this question makes sense. So the first result in this direction is a pretty negative result. So if you define the dilates of the function like this, so you just dilate, so it's f of r sub r, then you just dilate the domains a little bit, you multiply the variable z by r. And the theorem in 2016 tells us that there exists a non-extreme B, so B tilde, and a function G in the space H B tilde. So here it's B tilde, sorry, such that the limit, so the dilates of the function G diverges to infinity. So this is quite a wild behavior of the radial dilates, because we know in most classical spaces, the radial dilates will converge to the function in the norm of the space. Think of HP, think of disk algebra, think of any like classical Banach space of holomorphic function. In most of them, the radial dilates will converge to the function. So, but the Branges-Rovnyak spaces here is an exception to this quite a general rule. So the function G and tilde B are in fact explicit. So it's an explicit construction. So if you take B sub 0 to be this function, then tilde B is a product of this function B0 with a Blaschke product, the square of a Blaschke product. So with its zeros at 1 minus 8 to the power minus n. And the function G is a series of reproducing kernel for H2, and the reproducing kernels, they are at the point of the zeros of the Blaschke project B. So this is a quite wild behavior of the Branges-Rovnyak space for the radial dilates. So this, what it tells us is that so we're going to see here that the radial dilates is in fact what we call the Abel means of the Taylor series. So we can show that if we define the Abel means in this way, so we got the sequence of Taylor polynomials, and this is the Abel means, we can show that the Abel means is exactly the radial dilates. And in fact, we can show that the Abel means are in HB because they are equal to the radial dilates, and the radial dilates belongs to HB. So as a corollary, what we can say is that the Abel means, so if we choose B tilde and G, the Abel means will diverge to infinity, and as a consequence that the authors obtain is that the Taylor polynomials are unbounded in norm. So this is a consequence, and we're going to see it by an abstract theorem in another way that I'm going to show you a little bit later during the talk. So what we say here, the Abel means of its, so we say that this expression is the Abel means of the Taylor series. So the Abel means belongs to a wide family of summability methods. We call them the power series methods. So if we let X be a Banach space, so I'm going to present you some background on summability theory. So, so what is a power series method? Is you're given a power series P of R with a radius of convergence R, and all the coefficients in the power series are positive or 0, but the first one is positive. So the power series method P associated to this power series is defined formally by this new series, where Sn is a sequence in your Banach space X. So for here, because we want functions holomorphic in the unit disk, we're going to suppose that the power series here has a radius of convergence greater than or equals to 1. So for example, if you put Pn equals 1, then you got P of R, which is 1 minus R, so the inverse of 1 minus R. And this is exactly what we call the Abel summability method. This is the method I just presented you, the Abel means. So we say that the sequence S is summable with respect to a power series method P, or otherwise, in other words, P summable, if P of Rs, so the means induced by the power series method, is convergent for every RD in the radius, in the interval of convergence, and there exists a Y, so a vector Y, such that the means converges to Y as R approaches R, little r approaches capital R. And we say that P and Q are two power series methods. So we say that P is regular if we have the sequence Sn which converge to Y, then the means will converge to the same limit. So it preserves the limit of convergent sequence. So, and also P is included in Q if the means goes to Y. If the means induced by P goes to Y, then the means induced by Q goes to Y. So the method Q will preserve the sequence where they have P means, where they have convergent P means. And P is scalar included in Q if P is included in Q, but for scalar valued sequences. So this is the difference between included and scalar included. Here we restrict the sequence to be scalar valued. So an example would be that the the Taylor polynomials Sn, which is the partial sum of the Taylor series, they are included in the Abel means, the Abel summability method. This is an example of inclusion. So for non-extreme B, so now we know that the Abel means do not converge to F in the HB norm. So can we find another summability, power series summability method P, for which the Taylor polynomials will converge, will be P-summable with respect to P. So we know that the Abel doesn't work, the Abel method doesn't work. So, but in a paper of 1957, Bowen just shown that there is a more powerful method that includes the Abel method, is the logarithmic power series method. And I just want to mention that I just learned that the Dr. Bowen just died recently. So I just want to put him here because of him, I could write an article on this. And if he didn't work on logarithmic power series method, maybe I wouldn't be here talking about the motion-like spaces and summability. So I just want to thank him, and I would like to, if I could, like meet him in person to thank him. So I just put here just in memory of his work, and yeah, so it's a sort of homage to him. All right, so what is the logarithmic mean of the power series of the Taylor polynomials? So if you got a holomorphic function with its Taylor expansion, the logarithmic mean LR, so we will denote it by LR, is the following expression right here. So you see the Pn is exactly 1 over n plus 1. And what you get as a function is 1 over r log 1 over 1 minus r. So this would be the power series. And so if we have the logarithmic mean of a function, holomorphic function, then it is also a holomorphic function. And when b is non-extreme, the logarithmic mean belongs to HB also. And what we obtain as a result is a substantial like upgrade of the last result, because the Abel means are included in the logarithmic mean. So what you obtain is with the same b and g as the previous result for the Abel means, the radial dilates, we also had that the logarithmic mean diverge to infinity in the norm of HB. This is quite also surprising because we have a more powerful method and we still get no success. So it still doesn't work. So the result here is a consequence of an integral formula for what we call the LRF plus. So I'm just going to say, what is this function? So when you got a non-extreme b, there's also always an outer function a, which is uniquely defined if you suppose that at 0 is positive, such that we get this sort of Pythagorean identity almost everywhere on T. So we call A a Pythagorean mate in this case of 2B, of B. So a result by Donald Sarrazin is that if you got B a non-extreme and A be its Pythagorean mate, then a function f is in H2 belongs to HB if and only if there is a unique function f plus in H2 such that this identity holds. Here, T sub conjugate of B is the Toeplitz operator. So, and in this case, for any f in HB, we got this identity for the HB norm. And so what we found is that we can relate the function LRF plus in this theorem to the same function, but the Abel means. And when we got this integral formula for this function, we then apply the theorem of the authors back from 2016 on the Abel means. And we know that the Abel means of this function at 0 is always strictly greater than 0, and it goes to infinity. So we use this integral, in fact, converges in H2. And so it converges pointwise also. So we can evaluate this at 0. And since this is a positive kernel, and this goes to infinity, and this is always positive, we conclude that this also with some just a little bit work, that this goes to infinity at 0. And so we conclude that the HB norm of this, the logarithmic means, goes to infinity. So this is the first result that we obtain related to the logarithmic mean. And there is some consequences of this, because we can, in fact, get rid of a lot of summability method. So we define the generalized Abel means in the following way. So we got this big expression. So it's a generalization of the Abel means. And the method A alpha is always scalar included in the logarithmic means. This was a result by Borain. And if F is a holomorphic, then the generalized Abel means are always holomorphic. And if B is non-extreme, then the Abel means of a function in HB is always in HB. And as a corollary, we obtain this result. For every alpha strictly greater than -1, there exists a non-extreme B and a function F such that the generalized Abel means do not converge to F. So we got a generalization of the result regarding the Abel means, but now for a whole family of Abel summability method. And how did we get this result is from an abstract theorem for Banach spaces. So an abstract theorem for summability methods in Banach spaces. So if we got two regular power series method P and Q, two Banach spaces, and a sequence of operators from X to Y and an operator S, and if we have these conditions, so we converge pointwise on this dense subset of X, the sequence of operators is P summable to the operator S. pointwise, and P is scalar included in Q. So here we just require that we have scalar inclusion. Then the sequence Sn of X is Q summable. So we can deduce that from the summability of P, we can deduce the summability of Q. And from that, I'm going to skip here the proof, but it's a proof of contradiction. And so if we suppose that it is true that the Abel means, generalized Abel means converge to the initial function in HB norm, then this would imply that the logarithmic means would also converge to F, and this is a contradiction with our result. So with this abstract theorem, we can deduce that a whole family of summability method won't work. And this is quite surprising because we're trying to search, because the polynomial are dense, so we're trying to maybe try to find a summability method that would work, I think, but I think maybe there is one. So also in this hypothesis, we got a dense subspace of X. So one can ask if we can drop the hypothesis on the dense subset of W. In general, the answer is no. But if we suppose that X is reflexive, then we got what we say that the method P is weakly included in the method Q. So if we got that P is scalar included in Q and X is reflexive, then we can just conclude that P is weakly included in the method Q. And this is quite surprising. We didn't, like with the Banach space tools, like cannot deduce stronger result, like that P is included in the method Q. So here is the definition of weakly included. It's just you replace the norm convergence by the weak convergence. And so I'm going to end here. This is my last slide. So according to a result of Mashki and Ransford in 2019, I hope I got the date right. But when B is non-extreme, there is a sequence Tn of linear operators from HB to HB such that Tn is always a polynomial of degree at most n, and Tnf goes to f in the HB norm. So for the tilde B and G, so from the abstract theorem, we can deduce that all the Sejarro means do not converge to f, the radial dilates do not converge to G, the logarithmic means do not converge to G. But they've shown that there is such a linear polynomial approximation. So, and also the Taylor polynomials doesn't work. This, for the Sejarro means, this gives you a polynomial. So there's an open question yet that we don't know yet the expression of Tn. And I just want to mention in the paper in 2016, they constructed, so they gave an explicit constructive method to have a sequence of polynomials. So if you give an f, you can find the sequence of polynomials associated to this f, but this construction depends heavily on the function f. Here, the linear approximation scheme that we say, Tn, does not depend on the function f. So up to now, there is no known expression for the Tn, so this is yet an open question. So, and that's it. So thank you for your attention.
Thank you, Pierre-Olivier. So is there any question? So I have a question, maybe two, in fact. So the first one is you took the same B tilde than, yeah. So is there a lot of such B tilde which works, in fact, which doesn't work?
That's a great question. I didn't, like, the answer is, for now, I don't know. But if I think a little bit, maybe if you look at the construction of the, sorry, I'm just gonna go back. So here, when you see the construction of the function tilde b, you need this sort of control on the weight, on the zeros of the Blaschke product. So I think if you have a kind of decay on the zeros of the Blaschke product, maybe we can characterize such B, or at least a class of B. So yeah, so maybe there is something, yeah, if you can, and also here with this coefficient, so if you have, like, if you suppose that your coefficient is a certain order, and this one also a certain order, then maybe you can sort of characterize those types of B. But I don't know if it's going to be all the B's, but maybe you're going to have a bunch of B's that won't work. Yeah.
Okay. Okay, I see. Thank you. And my second question is the extreme case open or not?
For the extreme case?
Yeah.
So I think Alaman is here in the in the audience. So in the extreme case, what is happening? I'm saying Alaman because with the Malman they proved that the disk algebra is dense in HB. But for the extreme case, what is happening is that the polynomials are only a finite dimensional space in the Branges-Rovnyak space. So there's only a finite dimensional space of polynomials that is contained in HB. So the question doesn't make sense to approximate by polynomials, but recently in 2017, I think it was the beginning of my PhD. So Alaman and Malman proved that in 2017, yeah, proved that in the Branges-Rovnyak space, the disk algebra, so the set of the functions in HB and in the disk algebra is dense in HB. And up to now, the proof is not constructive. So we don't know what kind of elements that will approximate the function. And in the non-extreme case, there is a constructive proof. So we know, like I said, in these 5 authors in 2016, so Javad is here, and Tom also, my PhD advisor. In 2016, they prove that you can construct explicitly the polynomials that will approximate the function f. But the construction heavily depends on the function f. In fact, it is non-linear. So yeah. So up to now, there is no way to approximate the function f by polynomials, which will be in a linear fashion. Yeah.
Okay, thank you.
You're welcome. And just recently, for the extreme case, if you attend the talk of Bartosz and Malman, you're going to see that the Wiener, is it the Wiener? I think it's the Wiener algebra is dense in HB. So he improved his result with Alaman up to the Wiener algebra. So you can correct me. Anybody can correct me if I got this right or wrong. Yeah.
Okay, okay, thank you. Any other questions? So if not, let's thank Pierre-Olivier again.
Thank you for the invitation.